I will introduce the augmented base locus B plus of L is exactly the intersection for n from 1 to infinity, or all the divisor D belonging to this linear system L to the power n minus P upper star of Kx of D, and you can prove that this actually is the intersection of the same C, but for n from 1 to some n0 of t. So actually at some point is stabilized. It is nested one in another one, so at some point it must stabilize. Okay? So we need to study this B plus of L, and we have to look to B plus of L, the map over XF. So first things is we are lucky. This map, call it beta. Beta is not dominant, is not surjective. If beta is not surjective, we solve, because let Z be the image, and the bad P's are in Z. So we are everything is just defined over F, over the field. No. Now I have a projective bundle over XF. I'm working just on the generic fiber. I'm not looking to the... I used it to define it, but I didn't... But I'm not using it anymore. I used it to define and to show that the degree, the height with respect to the tautological bundle is the discriminant, but then I'm working just beta is some, no, B plus is a closed set inside the projective bundle of J upper star of omega 1 of X. This is a variety defined which has a map to XF. This is a map, this is a variety defined of a function field. And this, so now you are over a field. This is a closed set there. And you can see it. Okay? So if this map beta is not surjective, I solved my problem, because I have found an exceptional closed set. Now the problem, now I have to suppose, so you see, that beta is surjective. And I would like to see what happens. Okay, I can erase this. And to study beta, I will use a deep theorem by Nakamaye. I will state it in just this situation. which says that B plus of L is the union of V, where V is this, or degree of, with respect to L of V is equal to 0. So if you have a subvariety V of P of omega, you can consider the degree with respect to L of V is by definition the intersection of L to the power dim of V with V. This is not a trivial theorem, and which is very interesting because it gives you a numerical characterization of the augmented base locus of a line bundle. And okay, I will not prove this theorem, but I will use it. And now we come to our hypothesis. From the exact sequence which is here, let me call this x1 f. I see that x1 f is a divisor in P of omega 1 of x curly x, and O of P x1 f is equal to L. You see from this. From this you see that, okay. Arshon, chapter, second chapter. And so you can look to B plus L intersected avec x1f. This is just B plus L intersected avec x1f. And what happens is that this is the base locus, because of this characterization, of L restricted to x1f. The augmented base locus of L restricted to x. Why? Because this is exactly the set of the subvariety of x1f whose degree with respect to L is equal to 0. But now L restricted to x1f is ample. So this is the empty set. I repeat, there are no subvarieties of x1f whose intersection with L, whose degree with respect to L can be 0. Because in x1f, L is ample, so every subvariety has positive degree. So this subvariety must be of degree 0, because B plus L is of degree 0. In particular, degree of L of B plus L is equal to 0. So if you want degree L of B plus L intersected with x1L, x1F is equal to 0, because if you have this, so this is a variety of degree 0 inside x1F, but since this is ample, this must be empty. Ah, no. Yeah. So, I deduce that OP of x1F restricted to B plus of L OB plus L. Why? Because there exists a section of this line bundle which do not intersect the subvariety. So a section which is a unit everywhere. First. Second, since this is L, I deduce that L restricted to B plus L is equal to OB plus L. This because of this. Now I look to the exact sequence. I look to this exact sequence, I restrict it to B plus, and since B plus is contained in proj of this, I have here a quotient which is L. But this is O. So I have a map like this. And since this map is exactly the intersection with x1, this map is a split of Ks restricted to B plus. This quotient is given by the fact that B plus is a subvariety of proj of this vector bundle. This is trivial because I just proved it. So I have a map from this to this to this, gives to me a map from this to this, so a map from O to O, and this map is non-zero because it's exactly the evaluation onto the function on the function defined the divisor. So this map is an isomorphism. So this map is an isomorphism, so it's just giving a splitting of this exact sequence restricted to B plus. Okay? So a splitting of the exact sequence is restricted to B plus, say that the Kodaira-Spencer class of this exact sequence is 0 on B plus. Now you look to the property 2, which says if B plus dominates if B plus L dominates Bxf, then by property 2 implies that xf is isotrivial. But this is not a problem because for isotrivial variety we already see the problem. So B plus not dominating and we solve because we thought before that if it is not dominating, things are okay. Okay? So, okay. And this is the conclusion of Moriwaki theorem. And what time should I finish? In 10 minutes. Okay, what I like in this proof is that you see all the features of the function field case and also all the problems you will have in the function field case. So all the features is that you should relate things to the Kodaira-Spencer class. Second thing is that you should study a base locus to understand your problem. And third thing is exactly as in the problem, for instance, in hyperbolicity, is the problem is when this base locus dominates your variety. If it doesn't, you are solved. And of course, you can try to go to higher jet bundle, but the situation is more complicated because in higher jet bundles, the relative jet bundles are not anymore divisors inside the global jet bundles. So the situation becomes more and more complicated. Yeah, you go. You do exactly the same proof. Now I start my third hour because I planned to start. So the problem is what I can say about the third hour. So I will change topic because, and I will say just a little thing about positive characteristic. And tomorrow I will decide if I will speak about positive characteristic or about hyperbolicity. So why, first of all, just a few words, why we are interested to see also positive characteristic? You can say, but we don't care about. We just care about characteristic 0 and then perhaps in a future we'll be interested in positive characteristics. But this is not a good approach because as you see here we use many things just algebraic. But we also use some hidden characteristic 0 when we study Kodaira-Spencer class and when we use this fact that dominating isotriviality implies the isotriviality. So it is important to know when you study a problem in Diophantine geometry of a function field if your proof just use characteristic 0 method or is also is using also just abstract algebraic geometry which can be applied also in characteristic P. Because in characteristic P, many statements are false. So if your proof doesn't use at some point something which is peculiar of characteristic 0, you know that you are making a mistake, probably. So let's suppose that now our field F is Fp bar of a curve, a smooth projective curve. And to simplify things, yeah, okay. And what is interesting in characteristic 0 is that you have a Frobenius. And Frobenius is, as you know, okay, suppose that B is defined over Fp to simplify things. And Frobenius is just a map from B to B, which associates to an element A associate A to the power P. So it is the identity on the topological space, and on the sheaf is the power. The power. And why Frobenius is a little bit delicate? Because suppose that now X is a curve defined over Fp bar. Okay, Fp. And suppose that you have a morphism alpha from B to X. You can consider X as a curve over F. Simply X equal, or if you want, X tensor Fp bar F. So this has a model which is X times B over B, and you have a point which is the graph. Call this point P. Yeah. But now we can also change, we can also construct other points. We can construct the point, this Frobenius, we call it Fb. We can consider the point Pn equal to alpha composed by Fp, Fb, Fp identity. N, composite n times. Okay? And now the point is that the canonical sheaf of XF, this is just, here you have a projection over X, is just PR upper star of Kx. So you see that the degree of Pn upper star of Kxf is equal to the degree of alpha composed by Fb n upper star of Kx, and this morphism is a flat morphism of degree P. So this is equal to P to the power n times degree of alpha per star of kx. So it goes to infinity when n goes to infinity. And on the other side, the morphism which is here is the identity. So you have that the height with respect to kx of Pn goes to plus infinity, and the discriminant of Pn is constant. So I just constructed a counterexample to any hope of Vojta inequality in this context, because I found a sequence of points whose height goes to infinity and who has bounded discriminant. And in characteristic 0 you do not have Frobenius, but I would like to mention that in characteristic 0 you do the same thing, and you apply Hurwitz's formula, and you obtain that in the isotrivial case of curves, their height respected to kx of P is always less or equal than 2 genus of P minus 2, okay, divided by degree of P. So it's even better than 1 plus epsilon is 1. But in characteristic P, the inseparable morphism shows that you cannot hope this formula. Now time is over, but people can say, okay, but this is an isotrivial, very isotrivial case. It's a trivial case. It's really a product. Okay, I will decide tomorrow. I can also explain that there are, in the non-isotrivial case, you have some attention to do. You have to make careful, because you can find an inequality of Vojta type, but you cannot put 1 plus epsilon. You have to put something bigger. So this is near your question, and is non-isotrivial. In particular, you see again that isotriviality is weird. It's something that is strange in characteristic P, is even stranger than in characteristic 0. So its phenomena of isotriviality must be studied with a lot of carefully. Okay, perhaps I stop here.